somewhere deep inside every atom, there is a secret powerful enough to light stars, reshape planets, and quietly define your very existence. And yet, it hides in a space so small it is almost impossible to imagine. The atomic nucleus, a place where matter should not even be stable, where positively charged particles are packed so tightly together that, by all logic, they should violently repel and fly apart. And still, they don't. Instead, they remain bound, silent, holding within them energies millions of times greater than anything we experience in everyday life. So the question is not just what is nuclear physics, but why does this hidden world exist at all? And what is it really doing? Right now, inside everything around you. Here on Velarin's Sleepy Space Mysteries, we explore questions like this slowly, gently, letting each idea unfold like a quiet journey through the universe. In a recent Velarin video, we drifted through the life of stars and how they shine for billions of years. But tonight, we travel even deeper into the source of that light itself. Because the truth is, the story of stars begins here, inside the nucleus. And as we move forward, you may begin to notice something strange, that the smallest structures in reality are not simple at all, but layered with mystery, balance, and quiet tension. If that sounds like a journey you'd like to continue, take a moment to subscribe, gently tap the like button, and turn on the bell so you don't miss future explorations. If you enjoy these calm deep dives, you can also consider becoming a member, and let me know in the comments where you're listening from tonight. Now, let's begin. As we move deeper into this hidden world, it begins to feel less like a solid structure and more like a delicate balance that is constantly being maintained. The nucleus is not a rigid cluster of particles sitting quietly at the center of the atom. Instead, it behaves more like a dense, shifting system where motion, probability, and interaction quietly shape everything that happens within it. Protons and neutrons are not fixed in place like tiny marbles. They exist in a kind of blurred state where their positions are better described as regions of likelihood rather than exact points. This is one of the first clues that the nucleus belongs to the strange domain of quantum reality, where certainty fades and patterns take its place. And yet, even within this uncertainty, something remarkable happens. The nucleus holds together. This is where one of the central mysteries we introduced earlier begins to unfold again. If protons all carry positive charge, then they should repel each other strongly. The more protons you place into a small space, the stronger that repulsion becomes. In larger nuclei, this repulsive force grows immense, like pressure building inside a confined space. So why does the nucleus not simply break apart? The answer lies in a force that operates so quietly and so briefly in range that we never encounter it in everyday life. It is called the strong nuclear force. Unlike gravity or electromagnetism, which can act across vast distances, this force only becomes significant when particles are extremely close together. At distances comparable to the size of the nucleus, it becomes overwhelmingly powerful, binding protons and neutrons into a tight configuration. But there is something subtle about this force. It does not simply pull everything together endlessly. If it did, matter would collapse into an even denser state without limit. Instead, the strong force has a kind of balance built into it. At very tiny separations, even smaller than the usual spacing between nucleons, it becomes repulsive. This prevents particles from collapsing into a single point. At slightly larger distances, it becomes strongly attractive, holding the nucleus together. And beyond a certain distance, it fades away almost completely. This creates a quiet equilibrium. Each proton and neutron interacts mostly with its immediate neighbors, forming a kind of tightly packed community where stability emerges from local interactions rather than a single global force. This is why nuclei have a roughly constant density, no matter how large they become. Adding more particles does not compress the nucleus further. It simply expands the boundary outward. And here, another layer of mystery appears. Because not all nuclei are equally stable. Some combinations of protons and neutrons form structures that can persist for billions of years, while others exist only briefly before transforming into something else. This difference is not random. It reflects deeper patterns within the nucleus, patterns that physicists began to uncover when they noticed something unexpected. Certain numbers of protons or neutrons seem to create especially stable configurations. These became known as magic numbers. The term may sound almost poetic, but it reflects a real structural phenomenon. Inside the nucleus, nucleons arrange themselves into energy levels, somewhat similar to how electrons occupy shells around the atom. When one of these shells is completely filled, the nucleus gains an extra layer of stability, as if it has settled into a more comfortable configuration. This idea leads us to imagine the nucleus not as a chaotic cluster, but as a system with hidden order. Layers within layers, each contributing to the overall stability. But unlike the neat, predictable shells of electrons, nuclear shells are influenced by a far more complex set of interactions. The strong force, the motion of particles, and subtle quantum effects all combine to shape these internal structures. And still, even this is not the full picture. Because alongside this shell-like behavior, the nucleus can also act as a collective whole, can vibrate, stretch, and even rotate. In some cases, it behaves almost like a droplet of fluid, deforming slightly under internal forces. This dual nature, part individual motion, part collective behavior, is one of the reasons nuclear physics feels so layered and difficult to fully grasp. You may begin to notice a pattern forming here. Every time we try to describe the nucleus in a simple way, another layer of complexity reveals itself. It is not just a collection of particles. It is not just a fluid. It is both, and something more. And this brings us back to the quiet question we left earlier, now becoming clearer but not yet fully answered. If the nucleus is held together by such powerful forces, and structured in such intricate ways, then where exactly is the energy hidden? Why does rearranging these particles release such enormous amounts of energy, far beyond anything in chemistry? To begin answering that, we need to look not at the forces themselves, but at something even more subtle. Mass. Not just what mass is, but what it means, and what it might be quietly concealing. There is a quiet assumption most of us carry without ever noticing it, that mass is simply weight, that it is a measure of how much stuff something contains. A rock feels heavier than a leaf, so we say it has more mass. A planet has more mass than a grain of sand, so we imagine it simply contains more material. But as we move into the heart of nuclear physics, this familiar idea begins to soften and then gently unravel. Because inside the nucleus, mass is not just a measure of matter. It is also a measure of energy, quietly stored, almost like a memory of how the nucleus came to be. To begin to see this, imagine something very simple. Take a collection of individual protons and neutrons, separated from one another, floating freely. If you could somehow measure their total mass in that separated state, you would get a certain value. Now imagine bringing them together, allowing the strong nuclear force to bind them into a single nucleus. Intuitively, you might expect the mass to remain the same. After all, nothing has been added or removed, but something unexpected happens. The total mass of the bound nucleus is slightly less than the sum of its individual parts. Not by much, but enough to matter. This difference is not an error. It is not a missing piece. It is something that has been transformed. The lost mass has been converted into energy that was released when the nucleus formed, and energy that remains tied up in keeping it together. This is what physicists call binding energy. And this is the quiet answer to the question we've been circling. The energy inside the nucleus is not sitting there like a hidden battery waiting to be opened. It is woven into the very structure of the nucleus itself. It is the energy required to pull the nucleus apart, or the energy released when it forms. In other words, the stability of the nucleus is directly connected to how much energy is bound within it. And here, a deeper pattern begins to emerge. Not all nuclei store this energy in the same way. If we imagine arranging nuclei from the lightest to the heaviest, something interesting appears. Very light nuclei do not hold together very tightly. Their binding energy per particle is relatively low. As nuclei become heavier, this binding energy increases, reaching a peak around elements like iron. These nuclei are, in a sense, the most tightly bound, the most stable. But beyond this point, something changes again. As nuclei grow even heavier, the binding energy per particle begins to decrease. The strong force still holds things together, but the growing number of protons introduces increasing electrical repulsion. The balance becomes more delicate. Stability is still possible, but it is no longer as deep or as efficient. This single pattern, this gentle rise and fall of binding energy, quietly governs some of the most powerful processes in the universe. It explains why small nuclei can release energy by joining together. When light elements fuse into heavier ones, they move toward a more tightly bound state, releasing the excess energy. This is the process that powers stars, including our own sun. And it also explains why very heavy nuclei can release energy by splitting apart. When large nuclei break into smaller fragments, those fragments often sit closer to that peak of stability, again releasing energy in the process. Fusion and fission, two seemingly opposite processes, are both guided by the same underlying landscape. And this landscape is shaped by how energy is stored within mass itself. But there is something even more subtle here, because this energy is not easily accessible. If it were, matter would not remain stable. Every object around you would be constantly releasing enormous amounts of energy. The world would not have the quiet consistency that allows structures, life, and time to unfold. Instead, this energy remains locked behind barriers created by the same forces that hold the nucleus together. To release it, very specific conditions must be met. Nuclei must be pushed into new configurations, either by colliding with other particles or by existing in states that are already unstable. This brings us gently back to another question we introduced earlier. Why are some nuclei stable, while others are not? Why do some remain unchanged for billions of years, while others transform almost instantly? The answer lies not just in how much energy is stored, but in how that energy is arranged, and how easily the nucleus can move from one configuration to another. And this is where the story begins to shift from structure to transformation. Because within certain nuclei, the balance is not quite perfect. And when that balance is disturbed, even slightly, the nucleus begins to change, slowly, quietly, and sometimes inevitably. If we stay with this idea for a moment, that energy is woven into mass, and that stability depends on how that energy is arranged, then the behavior of unstable nuclei begins to feel less mysterious and more like a quiet consequence of imbalance. Not a dramatic failure, but a gentle correction. Because when a nucleus holds either too much energy or arranges that energy in an inefficient way, it begins to seek a more stable configuration. And it does this not all at once, but through subtle transitions that unfold over time. This is where the phenomenon of transformation begins to emerge, what we often call decay. But instead of imagining decay as something destructive, it may be more helpful to see it as a kind of rebalancing. The nucleus is not trying to fall apart. It is trying to settle, to move toward a state where its internal tensions are reduced. And the pathways it takes to do this are shaped by the same forces we have already encountered. The strong force, the electromagnetic repulsion, and something new that begins to quietly enter the picture. The weak interaction. Unlike the strong force, which binds nucleons together, or electromagnetism, which pushes protons apart, the weak interaction allows something more subtle to happen. It allows particles inside the nucleus to change their identity. A neutron can transform into a proton, or a proton into a neutron. And when this happens, other particles are released, light, elusive messengers that carry away energy and help restore balance. But before we go deeper into that transformation, there is another layer we need to gently uncover. Because not all instability leads immediately to change. In fact, many unstable nuclei can exist for surprisingly long periods before they transform. Some last seconds, others years, and some persist for billions of years before finally shifting into a new state. So what determines when a nucleus will change? The answer lies in something that feels almost paradoxical. Even if a nucleus has enough internal energy to move to a more stable state, it may still be prevented from doing so by an invisible barrier. Not a physical wall, but a kind of energy threshold that must be crossed. You can imagine it like a hill. On one side of the hill is the current state of the nucleus. On the other side lies a more stable configuration. But between them is a rise that must be overcome. In classical physics, if a system does not have enough energy to climb over this hill, it simply remains where it is. But in the quantum world, something extraordinary happens. Particles are not confined strictly by these barriers. Instead, they have a small but real probability of appearing on the other side, even if they do not have enough energy to cross in the usual sense. This phenomenon is known as quantum tunneling. It is one of the most subtle and powerful ideas in physics. And within the nucleus, it plays a central role in allowing transformations that would otherwise seem impossible. For example, in certain heavy nuclei, a small cluster of particles can slowly leak out of the nucleus through this tunneling process. From the outside, it appears as if the nucleus has emitted a fragment, even though that fragment never truly climbed over the barrier in a classical way. Instead, it simply appeared beyond it. This process is not predictable in the way we might expect. We cannot say exactly when a particular nucleus will undergo such a transition, but we can describe the probability. And when we observe large numbers of identical nuclei, a pattern emerges. A steady, predictable rhythm of transformation that defines what we call a half-life. Half-life is not a clock attached to individual atoms. It is a measure of collective behavior. If you begin with a large number of unstable nuclei, half of them will transform within a certain period of time. After that same period passes again, half of the remaining ones will transform, and so on. The process continues, gradually, quietly, like a fading echo. And here, something almost philosophical begins to take shape. At the level of individual events, the universe is uncertain. We cannot predict exactly when a single nucleus will change. But at the level of many, patterns become precise. Order emerges from randomness. Certainty arises from probability. This dual nature, uncertainty within order, is one of the defining features of the quantum world. And it connects back to everything we have explored so far. The nucleus is not a rigid object. It is a system of probabilities, forces, and energies, all interacting in ways that create both stability and change. Some configurations settle into long-lasting forms. Others remain only briefly before transitioning. But none of this happens in isolation, because every transformation releases something: particles, energy, motion, signals that travel outward and interact with the world beyond the nucleus. These signals carry information about what has occurred inside, allowing us, from a distance, to piece together the hidden processes within. And this is how we begin to understand the nucleus at all. Not by seeing it directly, but by listening to what it releases. And as we continue, we will begin to follow those signals more closely, to understand what they are, how they behave, and what they reveal about the quiet transformations happening deep within matter itself. As we follow these quiet signals outward, the particles and energy released from within the nucleus, we begin to realize something almost surprising. These emissions are not random noise. They are structured. Each type of transformation produces its own distinct signature, like a soft whisper carrying information about what has changed inside. And by learning to interpret these whispers, scientists have been able to reconstruct events taking place at scales far too small to ever observe directly. There are three primary ways a nucleus can release this internal imbalance, three gentle pathways through which it moves toward stability. Each one reflects a different kind of adjustment, a different way of redistributing energy and structure within the nucleus. The first is what we might imagine as the most tangible. In certain heavy nuclei, a small cluster of 2 protons and 2 neutrons can form inside the larger structure. This cluster is tightly bound, almost like a miniature nucleus within the nucleus. Over time, through the quiet process of quantum tunneling we explored earlier, this cluster can escape. When it does, the original nucleus becomes slightly smaller, slightly lighter, and often more stable. What is remarkable is not just that this happens, but how it happens. There is no dramatic buildup, no visible cracking or breaking. The cluster simply appears outside, having passed through an invisible barrier. From the outside, we detect it as a small, energetic particle moving away from the nucleus. But the deeper story is one of probability, of slow emergence rather than forceful ejection. The second pathway is more subtle, and it brings us back to the weak interaction we introduced earlier. In this case, the nucleus does not eject a cluster of particles. Instead, one of its internal components changes identity. A neutron can transform into a proton, or a proton into a neutron. When this happens, additional particles are released to conserve energy and balance, but the key transformation occurs within the structure itself. This process is especially important because it allows the nucleus to adjust the ratio between protons and neutrons. As we discussed before, stability often depends on maintaining the right balance between these two. Too many protons and the repulsive force becomes too strong. Too many neutrons and the configuration becomes energetically unfavorable. Through this quiet internal conversion, the nucleus can move closer to that narrow band of stability. And then there is a third pathway, one that is perhaps the most delicate of all. Sometimes the nucleus does not need to change its composition at all. Instead, it simply needs to release excess energy. In these cases, the nucleus transitions from a higher energy state to a lower one, emitting a burst of electromagnetic radiation in the process. This radiation is far more energetic than visible light, but the principle is similar. It is the nucleus letting go of energy, settling into a calmer state. Together, these three processes form a kind of language. Each tells us something different about the internal state of the nucleus, and by observing them, we can begin to map out the landscape of stability and transformation across all known elements. But there is something deeper here, something that connects back to the central theme we have been slowly unfolding. These transformations are not rare exceptions. They are everywhere, all around you, in the air, in the ground. Even within your own body, tiny nuclei are quietly undergoing these changes. Most of them are harmless, part of the natural background of the universe. Some occur so slowly that they feel almost timeless. Others happen more quickly, but still far beyond the scale of human perception. And yet, taken together, they form a constant, invisible activity, a kind of silent glow woven into the fabric of matter itself. This realization begins to shift our perspective. The world is not made of perfectly stable building blocks. It is made of structures that are stable enough, stable for now, but always carrying within them the possibility of change. Stability, in this sense, is not absolute. It is a temporary balance, maintained by the interplay of forces and energies we have been exploring. And this leads us gently into another question, one that has been quietly waiting beneath everything we have discussed. If transformation is so natural, so constant, then what role does it play on a larger scale? How do these tiny changes, happening deep within individual nuclei, connect to the broader story of the universe? Because the energy released in these processes, though small on the scale of a single atom, becomes immense when multiplied across vast numbers of nuclei. It can heat planets, illuminate stars, and even provide tools that allow us to see inside the human body. But it can also be harnessed, controlled, amplified. And when it is, the quiet balance inside the nucleus becomes something far more powerful, something capable of reshaping not just atoms, but entire civilizations. If we pause here for a moment and look back at the path we've taken, a quiet pattern begins to reveal itself. What once seemed like a solid, stable core at the center of the atom has slowly transformed into something far more dynamic. A place of balance, tension, probability, and continuous adjustment. The nucleus is not simply there. It is constantly maintaining itself, held together by forces that are both powerful and delicately limited in their reach. And within that balance, an energy is always present. Not in motion, not visible, but stored, waiting, encoded in the arrangement of protons and neutrons. This is the same energy we uncovered earlier, hidden within mass itself. The same energy that explains why binding occurs, why stability emerges, and why certain configurations feel more complete than others. But now we arrive at a turning point in our journey, because until now, everything we have explored has been passive. Nuclei forming, adjusting, slowly transforming over time. Natural processes unfolding quietly across vast stretches of time and space. But what happens when this balance is disturbed, not gently, but deliberately? What happens when we do not wait for the nucleus to change, but instead, we cause it to? To understand this, imagine a nucleus that is already close to instability. It is large, containing many protons, each one contributing to an increasing internal repulsion. The strong force still holds everything together, but the balance is fragile. Now imagine introducing a single additional particle into this system, something that does not feel the repulsive barrier as strongly. A neutron. Because the neutron carries no electric charge, it can approach the nucleus without being pushed away. It can slip inside, almost unnoticed, and become part of the system. But its arrival is not neutral in consequence. It adds energy. It changes the internal arrangement. It can push the nucleus beyond the threshold where its current structure can be maintained. And when that happens, the nucleus does not simply adjust, can split. This process is known as fission. And unlike the slow, probabilistic decays we explored earlier, fission can release a large amount of energy in a very short time. The nucleus divides into two smaller fragments, each carrying away kinetic energy, along with additional particles that continue to move outward. But there is a detail here that changes everything. When the nucleus splits, it often releases more neutrons. And those neutrons can go on to interact with other nuclei, triggering further splits, which release more neutrons, and so on. This creates what we call a chain reaction. At first, this may sound like a simple cascade, but the implications are profound. Because if each event leads to more than one subsequent event, the process grows. Not linearly, but exponentially. A quiet sequence becomes a rapidly expanding series of transformations, releasing enormous amounts of energy in the process. And here, for the first time, we see how the hidden energy within the nucleus can move from being a quiet background presence to something active, powerful, and potentially overwhelming. But this same process can also be controlled. If the number of neutrons is carefully managed, if some are absorbed or slowed down, the chain reaction can be stabilized. Instead of growing uncontrollably, it can be maintained at a steady rate, releasing energy gradually. This is the principle behind nuclear reactors, where the same fundamental process is used not for destruction, but for sustained energy production. And so, once again, we encounter a duality. The same physics, the same underlying forces, can lead to vastly different outcomes depending on how they are guided. But fission is only one side of the story. Because if energy can be released by splitting heavy nuclei, it can also be released by bringing light nuclei together. Earlier, we touched on this idea when discussing the binding energy curve. Light nuclei are not as tightly bound as those in the middle of the spectrum. When they combine, they move toward a more stable configuration, releasing energy in the process. This is fusion. And unlike fission, which begins with instability in large nuclei, fusion requires overcoming a barrier. Light nuclei, often positively charged, repel each other. To bring them close enough for the strong force to take hold, they must be pushed together with immense energy. This is what happens in the cores of stars, where temperature and pressure create conditions intense enough for fusion to occur. And once it begins, it can sustain itself for billions of years. So now the picture becomes complete. Energy hidden in mass, stability shaped by balance, transformation driven by probability, and power released through both splitting and merging. The nucleus is not just a structure. It is a source of energy, of change, and of connection between the smallest scales and the largest structures in the universe. And as we move into the next part of our journey, we will begin to follow that connection outward, beyond the atom, into stars, into time, and into the quiet processes that have shaped everything we know. If you're still here, gently listening as the story unfolds, let me know by commenting 1, so I know you're still drifting through this journey with me. As we move beyond the boundary of the atom, something subtle begins to shift in perspective. Up until now, The nucleus has felt like a hidden center, a quiet place where forces balance and energy rests. But as we follow the consequences of those internal processes outward, we begin to see that the nucleus is not isolated at all. Its behavior echoes far beyond its tiny scale, reaching into the fabric of time, matter, and even the history of the universe itself. And it begins with instability, not as a flaw but as a feature, because without unstable nuclei, much of what exists around us would never have formed. The gentle transformations we explored earlier, those slow adjustments driven by imbalance, are not rare events. They are part of a continuous process that shapes matter across vast stretches of time. Every decay, every quiet emission of energy, is a step in a longer journey, a movement toward configurations that are more stable, more balanced, more enduring. But here is where the mystery deepens. Why does instability exist at all? Why does the universe allow nuclei to exist in states that are not fully stable, only to transform them later? To begin answering this, we need to think not in terms of individual atoms, but in terms of populations, entire collections of nuclei evolving together. Imagine a vast cloud of matter, filled with many different isotopes, each with its own level of stability. Some are deeply stable, unlikely to change. Others sit closer to the edge, where transformation is more probable. Over time, the unstable ones gradually shift, releasing energy and particles, moving step by step toward more stable forms. This process is not chaotic. It follows patterns, the pathways that can be mapped, predicted, and understood. Chains of transformation unfold, where one nucleus becomes another, and then another, each step guided by the same underlying principles we have been exploring. These chains can stretch across multiple stages, sometimes involving many transitions before reaching a final, stable endpoint. And through this, something remarkable happens. Time itself becomes measurable, because each type of unstable nucleus transforms at its own characteristic pace. These processes act like natural clocks. Some tick quickly, marking short intervals. Others move slowly, measuring spans far beyond human experience. By observing how much of a particular isotope remains, compared to what it has transformed into, we can estimate how much time has passed. This is how we measure the age of ancient rocks, of fossils, even of the Earth itself. But it goes further. These same processes extend into the cosmos. In the aftermath of stellar explosions, newly formed nuclei are scattered into space, many of them unstable. As they decay, they emit signals that travel across vast distances. By detecting these signals, we gain insight into events that occurred long before our planet even existed. In this way, the quiet transformations within nuclei become a record, a memory of cosmic history. And yet, despite their importance, these processes remain almost entirely invisible to our senses. We do not feel them. We do not see them. They unfold silently, continuously, beneath the surface of everything we know. But their effects are everywhere. They contribute to the warmth inside planets, as slow decays release heat over billions of years. They shape the composition of the Earth, determining which elements remain and which have transformed. They even influence the environment around us, creating a background presence of radiation that, in small amounts, is simply part of the natural world. And here, another layer of complexity begins to emerge. Because while these processes are natural and often gentle, they also carry energy that can interact with matter in profound ways. When the particles and radiation released from nuclei pass through materials, they can deposit energy, alter structures, and trigger further changes. In living systems, this interaction becomes especially important, as it can affect cells and biological processes. This dual nature, quiet and constant, yet capable of significant impact, is part of what makes nuclear physics feel so deeply connected to both the smallest and largest aspects of existence. But there is still something unresolved. Because while we now understand that instability leads to transformation, and transformation leads to measurable effects, we have not yet fully explored the nature of what is being released. What exactly are these particles? How do they travel? And why are some of them so difficult to detect? Almost as if they pass through the universe without ever truly interacting with it. To answer that, we must follow these emissions more closely, tracing their paths as they move away from the nucleus and into the wider universe. If we follow one of these emissions, one of the quiet signals leaving the nucleus, we begin to notice that not all of them behave in the same way. Some are relatively easy to detect. They carry charge, they interact strongly with matter, and their presence can be traced through the paths they leave behind. Others, however, seem almost ghost-like. They pass through entire layers of material without leaving a trace, as if the universe barely notices them at all. And this difference is not accidental. It reflects the nature of the particles themselves and the roles they play in the process of transformation. Let us begin with the more tangible ones. When certain nuclei undergo transformation, they release particles that carry electric charge. Because of this charge, they interact readily with the atoms they encounter. As they move through matter, they can collide with electrons, transfer energy, and gradually slow down. In doing so, they leave behind a trail of interactions, a kind of invisible path that can be reconstructed with the right instruments. This is why some forms of radiation can be stopped relatively easily. A thin barrier, even something as simple as a sheet of material, can absorb them. Their journey is energetic, but short-lived. But then there are emissions that behave very differently. Some carry no electric charge at all. They move through matter without being pushed or pulled by the electromagnetic forces that dominate most interactions in the world around us. Because of this, they can travel vast distances without interruption. They pass through atoms, through entire objects, even through planets, with only the smallest chance of interacting with anything along the way. These are among the most elusive messengers in physics, and yet they are everywhere. Produced in enormous numbers during nuclear transformations, especially those involving the subtle processes of the weak interaction, they stream outward in all directions. Most of them pass through us constantly, unnoticed, unrecorded, leaving no effect. But occasionally, very rarely, one of them interacts. And when it does, it provides a glimpse into processes that would otherwise remain completely hidden. These particles carry away energy, helping to balance the transformations occurring inside the nucleus. But they also carry information about what changed, how it changed, and what conditions existed at the moment of transformation. Because they interact so weakly, they can escape from environments that would trap other forms of radiation. From the dense core of a star, from the violent collapse of a supernova, even from regions where light itself struggles to emerge. In this way, they act as messengers from the most hidden places in the universe. And this leads us to a quiet realization. Much of what we know about the universe does not come from what we see, but from what we detect indirectly, from signals that require careful interpretation, patience, and an understanding of the processes that produce them. The nucleus, in this sense, is not just a source of energy. It is a source of information. Every transformation sends out clues. Every emission carries a trace of the internal structure that produced it. And by collecting these clues, by studying patterns across many events, we begin to reconstruct a picture of something that cannot be observed directly. But there is another layer to this, because while some particles escape easily, others deposit their energy locally, interacting strongly with their surroundings. When they do, they can alter the materials they pass through. They can excite atoms, remove electrons, and create cascades of further interactions. This is how radiation can be detected, but it is also how it can influence matter. In living systems, this becomes particularly significant. The energy deposited by these interactions can affect molecular structures, sometimes altering them in subtle ways. Most of the time, these changes are repaired or have no lasting effect. But occasionally, they persist, becoming part of a longer chain of biological consequences. And so, once again, we encounter duality. The same emissions that allow us to study the universe, that provide insight into hidden processes, also carry the potential to alter the very systems they pass through. But beyond their interactions with matter, these particles reveal something deeper about the nature of reality itself. They show us that not all forces act in the same way, that some interactions are strong and immediate, shaping structure and stability, while others are quiet and rare, governing transformation and change. The weak interaction, in particular, operates almost invisibly, yet it is essential. Without it, many forms of nuclear transformation would not occur. The universe would be a very different place, more static, less dynamic. And this brings us back to the question we asked earlier. Why does the universe allow instability? Perhaps because instability is what allows change. And change is what allows complexity. Without these quiet transformations, the elements would not evolve. Stars would not produce the diversity of matter we observe. Planets, chemistry, even life itself might never have emerged. So what once seemed like imperfection, instability, becomes something essential. A quiet engine of transformation, operating deep within the smallest structures of reality. And as we continue, we will begin to see how this engine extends outward, shaping not just individual atoms, but entire stars, and the long unfolding story of the cosmos itself. As we continue drifting outward from the nucleus, following these nearly invisible messengers as they move through space. A deeper connection begins to form between the smallest processes and the largest structures in existence. What once felt like isolated transformations inside individual atoms now begins to resemble a vast, interconnected system, where each tiny event contributes to something much larger, something that unfolds across stars, galaxies, and time itself. And at the center of this connection lies a quiet truth that is easy to overlook, that the universe, in its present form, is not static, but constantly evolving through these subtle nuclear changes. To understand this, imagine the early universe, long before stars had fully formed, when matter existed in simpler states, dominated by the lightest elements. At that stage, the diversity of elements we see today did not yet exist. There was no carbon to form complex molecules, no oxygen to sustain life, no iron to build planets. The universe was, in a sense, incomplete, and it was through nuclear processes, through the balance of stability and transformation, that this complexity slowly emerged. Inside stars, under immense pressure and temperature, nuclei are pushed together in ways that overcome their natural repulsion. Their fusion begins quietly at first, as light nuclei combine to form heavier ones. With each step, energy is released, not in sudden bursts, but in a steady, persistent flow that allows stars to shine for millions, even billions of years. This process is not chaotic. It is regulated by the same balance we have seen before. If the reactions proceed too quickly, the star expands and cools. If they slow down, gravity pulls everything inward, increasing pressure and reigniting the process. A delicate equilibrium is maintained, one that allows stars to exist as stable sources of light and energy. But even this stability is temporary. As stars evolve, their internal conditions change. The simplest fuel, hydrogen, is gradually consumed. New reactions begin, forming heavier elements, each step requiring higher temperatures and greater pressure. Eventually, for many stars, this progression reaches a limit. The core can no longer sustain the balance between outward energy and inward gravity. And when that balance breaks, transformation accelerates. In some cases, this leads to a quiet fading. In others, it leads to an event so energetic that it reshapes entire regions of space. The outer layers of the star are expelled, carrying with them the elements that were forged deep within. These elements, once locked inside the star, are released into the surrounding space, where they become part of new clouds of matter. And from those clouds, new stars form, new planets, new systems. This cycle, driven by nuclear processes, repeats across the universe. It is slow, almost imperceptible on human timescales, but over millions and billions of years, it transforms the composition of the cosmos. Each generation of stars enriches the next, adding layers of complexity, building the elements necessary for more intricate structures to emerge. And here we begin to close one of the quiet loops we opened earlier. Why does instability exist? Because without it, this cycle would stop. If all nuclei were perfectly stable, if no transformations occurred, then the universe would remain locked in its simplest state. There would be no progression, no evolution of elements, no path toward complexity. Instability, in this sense, is not a flaw. It is a mechanism that allows the universe to change, to grow, to explore new configurations. And yet, this process is not uniform. Not all environments allow the same transformations. Some require extreme conditions, such as those found in the cores of massive stars or during their final moments. In these environments, nuclei can capture particles rapidly, forming highly unstable configurations that later decay into stable forms. These pathways create some of the heaviest elements known, elements that cannot be formed through ordinary stellar fusion alone. These processes are rare, but their impact is profound. They are responsible for the presence of elements like gold, uranium, and many others that play crucial roles in both natural systems and human technology. And once again, we see how the smallest interactions, the quiet changes within nuclei, scale upward to influence entire worlds. But there is something even more intimate about this connection, because the elements produced through these processes are not distant, abstract substances. They are the very materials that make up your body, the air you breathe, the ground beneath you, the carbon in your cells, the calcium in your bones, the iron in your blood. All of it was formed through nuclear transformations long before the Earth existed. In this way, the story of nuclear physics is not just a story about atoms or stars. It is a story about origin, about how the universe built itself from simplicity into complexity, using the quiet interplay of forces, energy, and transformation. And as we continue forward, we will begin to explore how these processes not only shape the cosmos, but also continue to influence it in the present moment, in ways both subtle and profound. Because even now, as you listen, those transformations have not stopped. They are still happening, slowly, quietly, everywhere. As we continue to follow this quiet unfolding, something begins to feel almost paradoxical. These nuclear processes are both unimaginably powerful, and yet almost completely invisible in everyday life. They shape stars, build elements, and stretch across cosmic time. But here, around you, everything feels stable, calm, unchanged. A table remains a table. A mountain remains a mountain. Your body feels continuous, not constantly transforming. And so a deeper question gently rises to the surface. If nuclear change is happening everywhere, why does the world feel so steady? The answer lies in scale and in patience. Most nuclear transformations occur either incredibly slowly or in environments far removed from our daily experience. The unstable nuclei around us often decay at such gradual rates that their changes are imperceptible moment to moment. A single atom may wait thousands, millions, or even billions of years before transforming. And even when it does, the effect is so small, so localized, that it blends into the background of everything else. But when we gather many atoms together, when we look at vast collections of matter, those tiny changes accumulate. And over long periods of time, they begin to shape the world in ways that are subtle, but profound. Deep within the Earth, for example, nuclear decay quietly releases heat, not in sudden bursts, but as a slow, steady flow. This heat contributes to the movement of material beneath the surface, driving processes that shape continents, create mountains, and fuel volcanic activity. Without it, the planet might have cooled and solidified long ago, becoming far less dynamic than it is today. So even beneath your feet, the quiet transformations of nuclei are still at work. And yet, the same processes that gently warm a planet can also become far more intense under different conditions. When nuclear transformations occur in rapid succession or in concentrated environments, the energy they release becomes impossible to ignore. This is what we glimpsed earlier with fission, and what we will soon explore more deeply with fusion. But before we move fully into those extremes, there is another layer of subtlety to uncover. Because nuclear transformations do not only release energy, they also reshape identity. Each time a nucleus changes, it can become a different element. A transformation in the number of protons alters the very nature of the atom. What was once one element becomes another, with entirely different chemical properties. This means that nuclear processes are not just rearranging energy. They are actively rewriting the composition of matter. This idea carries a quiet weight, because it means that the material world is not fixed at its deepest level. It is capable of changing its identity, given the right conditions and enough time. And while these changes are usually slow and rare on human scales, they are fundamental to the long-term evolution of matter across the universe. This brings us back to another thread we introduced earlier, the idea that nuclei follow pathways, chains of transformation. One isotope becomes another, which becomes another, each step guided by the interplay of forces and probabilities. These chains eventually lead toward stable configurations, but the path itself can be long, complex, and filled with intermediate stages. And each stage leaves its mark. By studying these transformation chains, scientists can trace the history of materials. They can determine how old something is, where it originated, and what processes it has undergone. In this way, nuclear physics becomes not just a study of structure and energy, but a tool for understanding time itself. But there is something even more subtle hidden within these processes. Because while we often think of time as something that flows smoothly and continuously, nuclear transformations reveal a different perspective. At the level of individual atoms, change does not occur gradually. It happens in discrete events. A nucleus exists in one state, and then suddenly it is in another. There is no in-between, no slow transition that we can observe, just a shift governed by probability. And yet, when we look at many atoms together, these discrete events blend into smooth curves, predictable patterns, steady decay rates. Once again, we see this dual nature, randomness at the smallest scale, order at the largest. This pattern echoes throughout everything we have explored. Balance and instability, structure and motion, randomness and predictability. The nucleus embodies all of these at once. And as we move closer to the final part of our journey, we begin to see how these principles extend into the most powerful phenomena in the universe. Because when the conditions are right, when nuclei are pushed beyond their quiet equilibrium, the energy we have been tracing all along does not remain hidden. It emerges, not as a whisper, but as something far more luminous. And in that emergence, we begin to understand not only how stars shine, but how the universe itself continues to transform, even now in the quiet vastness of space. As we reach the end of this part of our journey, it becomes clear that what began as a question about the nucleus has quietly expanded into something much larger. We started by asking why atoms hold together, why energy is hidden within them, why some remain stable while others slowly change. And now those questions have led us outward into time, into stars, into the very processes that shaped everything we know. But there is one final layer to uncover here, one last thread that ties these ideas together before we move on. Because throughout everything we've explored, there has been a quiet tension, a balance between what is stable and what is not, between what endures and what transforms. And this balance is not fixed. It shifts depending on conditions, on environment, on the history of the matter itself. Some nuclei, as we've seen, are deeply stable. They sit in configurations that require enormous energy to disrupt. These nuclei can persist for billions of years, effectively unchanged, forming the foundation of matter as we experience it in daily life. They give the world its sense of continuity, its reliability, its calm surface. But others exist closer to the edge. They carry just enough imbalance that, given time, they will transform. Not immediately, not dramatically, but inevitably. And this inevitability is what gives nuclear physics its quiet sense of motion. Even in a world that appears still, change is always present, waiting, unfolding at its own pace. And then there are those rare conditions, those extreme environments, where the balance shifts completely, where nuclei are no longer gently adjusting, but rapidly transforming, where the barriers we spoke of earlier are overcome not by probability alone, but by immense energy. In these environments, nuclear processes accelerate. Reactions that would take thousands or millions of years under normal conditions can occur in fractions of a second. Chains of transformation unfold rapidly, releasing vast amounts of energy and reshaping matter on a scale that becomes visible, even overwhelming. These are the conditions found in the hearts of stars, in the final moments of massive stellar collapse, in the collisions of dense cosmic objects. And it is here that the quiet principles we have been exploring reveal their full power. Because the same forces, the same balance of attraction and repulsion, the same relationship between mass and energy, operate everywhere. The difference is only in scale and intensity. And this realization brings us back, gently, to ourselves. Because while these processes shape stars and galaxies, they also exist within the matter that forms your body. The atoms that make up your cells are the result of countless nuclear transformations that occurred long before you were born. They carry within them a history that stretches back through stars, through explosions, through the gradual evolution of the universe. And even now, those atoms are not completely still. Within them, in rare cases, tiny transformations may still occur. Small, almost imperceptible events that remind us that matter is not frozen, but alive with possibility. This does not make the world unstable. It makes it dynamic. It means that beneath the calm surface of reality, there is always a quiet process of becoming, a slow unfolding that connects past, present, and future. And perhaps this is the deeper perspective that nuclear physics offers. That stability is not the absence of change, but a balance within it. That energy is not separate from matter, but part of its very nature. And that even the smallest structures in the universe carry within them the potential to shape something far greater. As we move into the final part of our journey, we will begin to focus more directly on these powerful transformations, on the moments when the hidden energy of the nucleus is no longer quiet, but revealed. We will explore how this energy powers the stars, how it can be harnessed, and how it has influenced both the evolution of the universe and the path of human civilization. But for now, let this thought settle gently, that within every atom, there is a story of balance, of tension, of quiet change unfolding across time. And that story is still being written. If you've stayed with this journey all the way to this point, slowly drifting through these ideas, let me know by commenting too, so I know you're still here, still listening, still exploring. As we enter the final stage of this journey, the quiet story we have been following begins to change in tone. Until now, nuclear physics has felt like something hidden, something subtle, unfolding slowly beneath the surface of reality. A balance of forces, a gradual shifting of structures, a calm and almost silent evolution. But here, we begin to approach the moments when that silence breaks. Not violently at first, but noticeably, because when the conditions are right, the energy stored within the nucleus does not remain hidden. It reveals itself. And one of the most striking ways this happens is through a process we briefly touched on before: nuclear fission. But now, instead of seeing it as a concept, we can begin to understand it as a continuation of everything we have already explored. A natural consequence of imbalance, taken to its extreme. Imagine again a very heavy nucleus, one with many protons, each one contributing to an internal tension that is constantly being held in check by the strong force. This nucleus is not unstable in the immediate sense. It can persist, it can exist, but its balance is delicate. It is like a structure that holds together, not because it is perfectly stable, but because the forces within it are carefully counteracting one another. Now imagine that a small disturbance is introduced. A neutron enters the nucleus. As we explored earlier, the neutron does not face the same repulsion as charged particles. It can approach closely, slip inside, and become part of the system. But this addition is not neutral. It changes the internal energy, distorts the balance, and can push the nucleus into a configuration that is no longer sustainable. And at that moment, something remarkable happens. The nucleus begins to stretch, not physically in a way we could see, but in its internal configuration. It shifts from a compact shape into something more elongated, as if it is being pulled apart from within. The repulsive forces between protons begin to dominate in certain regions, while the strong force struggles to maintain cohesion. And then, the balance breaks. the nucleus divides into two smaller fragments. This division is not symmetrical. The fragments are often of different sizes, each carrying away part of the original structure. But what matters most is what accompanies this division. A release of energy, not gradual, not subtle, but immediate and significant. The fragments move apart with high speed, carrying kinetic energy. Additional particles are emitted, and once again we see the same principle: mass transforming into energy. But there is a detail here that connects this process back to everything we have already learned. The fragments that result from fission are not perfectly stable. They themselves often carry excess energy, excess imbalance, and so they continue to transform. Chains of decay follow, releasing additional energy over time. The initial event is only the beginning of a longer sequence, one that gradually leads toward more stable configurations. And then there are the neutrons. When the nucleus splits, it does not simply divide into two pieces. It also releases additional neutrons. And these neutrons, like the one that initiated the process, can move outward and interact with other nuclei. If they encounter other heavy nuclei under the right conditions, they can trigger further fission events. This is where the process becomes something more than an isolated transformation. It becomes a chain, one event leading to another, and then another, each releasing energy, each producing more neutrons. If the conditions allow, this chain can sustain itself. It can continue without external input, driven purely by the interactions between nuclei. And this is where the quiet potential of nuclear energy becomes something much more visible. Because a controlled chain reaction can produce a steady release of energy, one that can be harnessed, directed, and used. But an uncontrolled chain reaction grows rapidly, exponentially, releasing energy in a very short time. The physics is the same. The difference lies in control. And this brings us back to a theme that has quietly followed us throughout this journey. The idea that the nucleus is not simply powerful, but sensitive. That small changes in configuration can lead to very different outcomes. That balance is everything. Fission is not an anomaly. It is the natural expression of the principles we have been exploring, taken into a regime where the stored energy is finally released in a way we can clearly observe. And yet, this is only half of the story. Because while heavy nuclei can release energy by breaking apart, light nuclei can release energy by coming together. And in the next step of our journey, we will move from the splitting of atoms to something even more fundamental, the process that lights the stars. If fission is the story of heavy nuclei reaching a breaking point, then fusion is something very different. It is not about imbalance tearing matter apart, but about overcoming resistance to bring matter together. And in many ways, it is even more profound, because while fission reveals the hidden energy within unstable structures, fusion reveals the path toward deeper stability. And in doing so, it becomes the engine that lights the universe itself. To understand fusion, we return to something we uncovered earlier: the idea that not all nuclei are equally stable. There is a kind of landscape, a quiet pattern in how tightly nucleons are bound together. Light nuclei, such as those made of only a few protons and neutrons, are not as tightly bound as those in the middle range. This means that when they combine, when they move toward a more stable configuration, energy is released. But unlike fission, this process does not happen easily, because before two nuclei can join, they must first come extremely close together. And here, the familiar challenge returns. Protons carry positive charge, and like charges repel. This repulsion creates a barrier, one that prevents nuclei from simply merging under normal conditions. Even if they are moving quickly, even if they approach one another, they are often pushed apart before the strong nuclear force can take hold. So for fusion to occur, something must overcome this barrier. In stars, this is achieved through immense temperature and pressure. At temperatures of millions of degrees, particles move with tremendous speed. Collisions become more frequent, more energetic. And while most of these collisions still result in separation, a small fraction succeed. Through a combination of high energy and quantum tunneling, nuclei manage to come close enough for the strong force to bind them together. And when that happens, the result is transformative. Two light nuclei merge into a heavier one, and in the process, a small amount of mass is converted into energy. This energy does not remain hidden. It is released as radiation, as motion, as heat. And when this process occurs countless times, continuously, it produces the steady glow of a star. This is how the sun shines, not through burning in the chemical sense, but through a quiet, ongoing sequence of nuclear transformations at its core. Every second, an immense number of fusion events take place, each one releasing a tiny amount of energy. But together, they add up to something vast, enough to sustain the light and warmth that reaches Earth. And yet, what makes fusion so remarkable is not just its power, but its persistence. Unlike fission, which depends on specific conditions and materials, fusion can continue as long as the necessary environment is maintained. In stars, gravity provides this environment. The immense mass of the star creates pressure that holds the core together, allowing the reactions to continue over incredibly long periods of time. But even this balance is not permanent. As fusion progresses, the composition of the core changes. Hydrogen is gradually converted into helium. Over time, the available fuel shifts, and new types of fusion reactions begin. Each stage requires higher temperatures, greater pressure, and more extreme conditions. Eventually, the star reaches a point where further fusion becomes difficult or impossible to sustain. And at that point, the story changes again. But before we follow that path, there is something important to notice. Fusion is not just a process that produces energy. It is a process that creates elements. Each fusion reaction builds something new. Hydrogen becomes helium. Helium can become heavier elements under the right conditions. And through successive stages, stars act as forges, constructing the elements that make up the universe. This brings us back to a realization we touched on earlier, but now it feels more complete. The matter around you is not primordial in its current form. It has been shaped, refined, built through countless nuclear processes across cosmic time. The elements that make up your world were once inside stars, formed through fusion, and later dispersed into space. Without these processes, the universe would remain simple, lacking the diversity that allows for planets, chemistry, and life. Fusion, in this sense, is not just about energy. It is about creation. It is about the transformation of simplicity into complexity, driven by the same fundamental forces we have been exploring all along. And yet, there is a quiet challenge hidden within this. Because while fusion happens naturally in stars, recreating it elsewhere is not easy. The conditions required are extreme, and maintaining them is difficult. Without the immense gravitational pressure of a star, sustaining fusion becomes one of the greatest challenges in physics and engineering. But the effort continues, because if fusion can be controlled, if its steady release of energy can be harnessed, it offers something remarkable, a source of energy that mirrors the stars themselves, abundant, powerful, and fundamentally different from the processes we rely on today. And so, once again, we see the dual nature of nuclear physics, a story that stretches from the quiet interior of atoms to the blazing cores of stars, to the ambitions of human civilization. And as we move toward the final segments of this journey, we will begin to bring these threads together, exploring not just how these processes work, but what they mean for the universe and for us. As we move deeper into this final part of the journey, something begins to settle into place. The processes we have explored, fission and fusion, are no longer separate ideas. They begin to feel like two expressions of the same underlying truth, that matter seeks balance, and in doing so releases energy. Whether by splitting apart or coming together, nuclei are always moving toward configurations that are more stable, more complete. And in that movement, the hidden energy within them becomes visible. But now we arrive at a question that feels both scientific and deeply human. If this energy exists, if it can be released, what does it mean for us? Because unlike stars, which follow these processes naturally, we have learned to interact with them, to initiate them, to guide them, and in doing so, we have stepped into a relationship with the fundamental forces of nature that is both powerful and delicate. Let us begin with fission, because it was here that this relationship first became clear. When scientists discovered that heavy nuclei could be split, releasing energy and additional neutrons, they realized something extraordinary. Under the right conditions, this process could sustain itself. A chain reaction could be created not as a natural background process, but as something engineered, controlled, or uncontrolled. And this realization changed everything. Because for the first time, the energy hidden within the nucleus was no longer just a feature of the universe. It became something that could be accessed, something that could be used. In controlled environments, this led to the development of nuclear reactors, systems designed to manage the chain reaction carefully, to ensure that each fission event leads to just enough subsequent events to maintain a steady output. Not too fast, not too slow. A balance once again becomes the key. By absorbing excess neutrons and regulating the conditions within the system, the reaction can be kept stable, producing heat that can be converted into electricity. In this form, nuclear energy becomes a tool, a way of converting the deep, hidden energy of matter into something usable, something that can power cities, sustain infrastructure, and support modern life. And in doing so, it reveals just how much energy is truly stored within the nucleus. Even small amounts of material can produce vast quantities of energy, far beyond what is possible through chemical processes. But the same principle carries another possibility. If the chain reaction is not controlled, if it is allowed to proceed rapidly, the energy is released in a very short time. The same process that can gently power a city can also produce an intense burst of energy, concentrated and immediate. And this dual nature introduces a level of responsibility that is difficult to ignore, because the physics does not change, only the way it is applied. And this brings us to a broader reflection, one that has quietly followed us since the beginning. That understanding is not neutral. To understand something deeply is also to gain the ability to influence it. And when the subject is something as fundamental as nuclear energy, that influence carries weight. It requires choices. It requires care. It requires an awareness of both potential and consequence. But alongside fission, there is fusion, and with it, a different kind of possibility. Fusion, as we have seen, powers the stars. It produces energy not through the breakdown of heavy nuclei, but through the union of light ones. And unlike fission, it does not rely on a chain reaction in the same way. It requires continuous conditions, high temperature, high pressure to sustain itself. If those conditions are not maintained, the process simply stops. This characteristic makes fusion fundamentally different in its behavior. It is difficult to start, difficult to sustain, but also inherently limited in how it can proceed. There is no runaway chain reaction in the same sense. The process depends entirely on maintaining the right environment. And this has led to a long-standing goal: to harness fusion as a source of energy, to recreate in a controlled way the same processes that power the sun, to generate energy that is abundant, steady, and based on fuel that is widely available. The potential is immense, but so is the challenge. Creating and maintaining the conditions required for fusion, without the aid of a star's gravity, is one of the most complex problems in science and engineering. And yet, progress continues, because the promise of fusion is not just about energy. It is about alignment. Alignment with the processes that already exist in the universe. A way of drawing energy not from breaking matter apart, but from guiding it toward greater stability. And so, as we stand at this point in the journey, something becomes clear. Nuclear physics is not just about understanding the nucleus. It is about understanding possibility. The possibility that within the smallest structures of matter lies a vast reserve of energy. The possibility that this energy can shape stars, planets, and civilizations. And the possibility that how we choose to engage with it will shape the future in ways we are only beginning to understand. And as we move into the final moments of this exploration, we will begin to step back to reflect and to see how all of these ideas come together, not as isolated concepts, but as part of a single quiet story. A story written in the language of the nucleus, but echoing across the universe itself. As we begin to slow down, to step back from the details, something larger comes into view. The journey we've taken, from the quiet interior of the nucleus to the blazing cores of stars, begins to feel less like a series of separate ideas and more like a single continuous thread. A thread that runs through everything. Through matter, through energy, through time itself. At first, the nucleus seemed small, almost insignificant. A tiny region at the center of the atom, hidden from direct observation, distant from everyday experience. But as we followed its behavior, as we listened to its quiet transformations, it revealed something unexpected. That within this small space lies a set of principles that shape the entire universe. Balance and tension, stability and change, energy and structure. These are not just properties of the nucleus. They are patterns that repeat at every scale. We saw how protons and neutrons arrange themselves not randomly, but according to deeper rules. How forces that are invisible to us maintain a delicate equilibrium, allowing matter to exist at all. And how even slight imbalances can lead to transformation, sometimes slow and subtle, sometimes powerful and immediate. And then we followed those transformations outward. We saw how instability allows elements to change, how decay becomes a clock that measures time, how particles escaping from the nucleus carry information across vast distances. We saw how stars use these same principles to shine, to build the elements, to shape the cosmos over billions of years. And through all of this, one idea quietly persisted. That nothing is truly static. Even the most solid objects, the most stable materials, are composed of structures that are, at their deepest level, dynamic. Not chaotic, not constantly changing in ways we can perceive, but quietly evolving, held in balance by forces that are always present. This perspective changes something subtle in how we see the world, because it suggests that stability is not a permanent state, but a condition that is continuously maintained, a balance that holds until it shifts. And when it does, the change is not arbitrary. It follows the same patterns, the same pathways, the same principles that have guided everything from the beginning. And this brings us to a kind of quiet realization that the energy within the nucleus, the energy that powers stars and shapes matter, is not separate from us. It is part of the same universe we inhabit. The same processes that occur in distant stars also played a role in the formation of the atoms around you. The same forces that bind nuclei together are present in every piece of matter you touch. The same transformations that unfold over cosmic time are, in small ways, still happening even now. And yet, despite all of this, the universe feels calm, feels stable. It allows for continuity, for structure, for life to exist and persist. This is perhaps the most remarkable aspect of all, that beneath immense power, there is restraint, that beneath constant change, there is order. And that this balance has held long enough for complexity to emerge, for stars to form, for planets to develop, for life to arise. and for awareness itself to look back and begin to understand. As we approach the end of this journey, we begin to move away from explanation and toward reflection. Because beyond the equations, beyond the experiments, beyond the theories, there is something quietly profound in what nuclear physics reveals. That the universe is not built from static pieces, but from relationships. Relationships between particles, between forces, between energy and form. And these relationships are what give rise to everything we see. The light of the stars, the warmth of the earth, the elements within your body, all of it emerging from the same underlying principles. And so, as the pace begins to slow, as the ideas settle, there is nothing more to analyze, nothing more to break apart, only something to notice, that within the smallest spaces, the universe has written its deepest rules. And in understanding them, even gently, even partially, we begin to see the quiet unity behind everything. And now, as everything begins to settle, we arrive at the quiet edge of this journey. Not an ending in the usual sense, but a gentle fading, like the last light of a distant star slipping beyond the horizon. The ideas remain, but they soften. The details dissolve, leaving only a calm, spacious understanding behind. If you think back to where we began, it was with a simple question. What lies inside the atom? A question that seemed small, almost contained. But as we followed it patiently, step by step, it opened outward. It led us into forces we cannot see, into energies we cannot feel directly, into processes that stretch across billions of years. And now, at the end, the answer feels less like a definition and more like a perspective, that inside the atom, there is no stillness, only balance, a quiet, continuous balance between forces pulling together and forces pushing apart, between stability and the possibility of change. And within that balance, the energy is always present, not as something separate, but as something woven into the structure itself. And yet, despite all of this hidden activity, the world remains calm. The objects around you do not tremble with visible energy. The ground beneath you does not pulse with constant transformation. Instead, everything feels steady, reliable, at rest. And this is not because nothing is happening, but because everything is happening in harmony. The forces are balanced. The changes are measured. The energy is contained until it is needed, or until the conditions allow it to emerge. And this, perhaps, is the quiet lesson that remains, that the universe does not need to be still to feel stable. It only needs to be in balance. As you rest here, listening, you might imagine the atoms around you, not as solid points, but as tiny systems, each with its own internal story. Protons and neutrons held together in delicate arrangements. Energy stored quietly within their structure. Occasional transformations unfolding far too slowly to notice, yet always present. And beyond them, the larger picture continues. Stars still burn far away, sustained by the same processes. Deep within their cores, Fusion continues moment by moment, releasing light that will travel across space for years, centuries, before reaching distant worlds. Somewhere, even now, new elements are being formed, new matter is taking shape, continuing the long story that led eventually to this moment. And all of it connected, from the smallest nucleus to the largest galaxy. Not separate pieces, but parts of a single unfolding system. You don't need to hold all of this in your mind. You don't need to follow every detail. It is enough to sense it gently, that beneath everything familiar, there is depth. That beneath stillness, there is motion. And that within the smallest spaces, the universe is quietly alive. So as the thoughts begin to drift, as the details fade into something softer, you can let the story settle. Let it become less about understanding and more about feeling the quiet continuity of it all. The atoms remain, the balance holds, the universe continues, slowly, calmly, without urgency. And you, for this moment, are simply part of it, resting within it, carried along by the same gentle laws that guide the stars, that shape matter, that hold everything together. There is nothing you need to do, nothing you need to solve, only to rest and let the quiet of it all remain. And if you are still here, still listening, slowly drifting at the edge of sleep, you can leave a soft 3 in the comments, just to mark that you made it all the way through this journey. For now, the story fades, but the universe continues.